So let us see what happens. Okay. So what I want to talk about today, okay, uh, well, this is literally the 100th year of Heisenberg's work on matrix models. Okay, somebody else mentioned it. I think Rajiv mentioned it. So my remembrance at that time, then very soon afterwards, there occurred a series of events. Schrodinger, then came along the Dirac, all kinds of things happened. And the idea that there is a collapse of the wave packet seems to have been introduced by Heisenberg, from what I understand. In order to, it's like a band-aid, because he didn't know what to do and he wanted to keep going. So he made a band-aid and said, you said classical physics. And that band-aid seems to have persisted down to this day when people talk about collapse of wave packets. So I will express, I will make remarks on that and also express my own opinion on this collapse of wave packet business. There are many unsatisfactory aspects about the nature of cognition from quantum mechanics, and that will be the subject of this matter. But it will also touch very much upon what Chetan was talking about and other things like what Sachin was talking about super selection rules, and also about this, what people call for mysterious reasons, topological insulators. I don't know why they are topological, but they call it like that. So I will mention that also. Why am I saying topological? Why topological? It has a metric which is used extensively in the calculations. Okay, it's only a name, so it's okay. So let me keep going. Okay. So this, as I say, this is the 100th year, and I want to start off by quoting a very perceptive remark by, well, a remark which I like very much due to Marx, which comes from the 11th thesis on Feuerbach. There was a debate going on the nature of reality between Feuerbach, Marx. Engels, I think, still was not in the game. And the 11th thesis, which was, I think, the prelude to the German ideology book, that's my recollection, says that the philosophers have only interpreted the world in various ways. The point is to change it. So if I take that remark and expand on it, you see that, in fact, quantum mechanics in this 100 years has already done it. Okay? It has revolutionized the nature, many aspects of our lives, our perception, our cognition about nature, by various discoveries in atomic, molecular, nuclear, and other branches of physics. Okay? But there are still very deep questions which are being debated in the literature about measurement theory. You might know very not so long ago about de Sitter spaces, where there are horizons which are dependent upon the observer for a given background. And there were sector papers by Ed Witten, Roberto Longo, Chandrasekharan, and Pennington, okay, where they were trying to tackle this problem. So this is as late as now by people who are very much involved in this nature of quantum field theory. But I want to claim now that it is much deeper problem. Okay? And it is known. It is known in the literature. It's just that due to Bell's influence, there is something for FAPP. That's what my friends quote. What is FAPP? For all practical purposes, let's collapse the wave packet. That is what is called FAPP. So, in this drawing, I'll tell you what this deep problem is. And this work is really a drawing work with Sasha Pinzul, who is in Brasilia. Of course, clearly, he's of Russian origin. And we will show, I will argue, that in any standard gauge theory, there is holography. And where the boundary states are boundary state encode information on bulk states. This is not what I will not talk. I will not talk about ADS safety business, but there is entanglement, and this entanglement is of such a character that the boundary measurements give you information on the bulk measurements, and also the boundary algebra. I'm not messing around with things. Is an abelian algebra, and we will argue in a minute that abelian algebras are essentially classical algebras. They codify classical algebras. So this process has been called Bohrification, because Bohr already anticipated in his original papers that for large quantum numbers, there emerges he was saying, he did not know algebraic language, but he was saying that a classical physics will emerge for large n. Okay? So he was already arguing at that time how classical physics emerges from a quantum situation, and we will talk about it more. Okay? And I'll try to show you that this happens in canonical gauge theories, and it is already implicit in the work I did with Sachin, I think, long ago. But we did not appreciate. We did mention it, but we did not appreciate the significance of our observations. So, as a side thing which I have, side remark which I will have no time to expand upon, there are questions that we can talk about it. We will see that infinite number of non-abelian, conservation laws automatically emerge from this calculation. There are infinite number of conservation laws that cannot be described by Lagrangian, by old Noether's principle at all, but they commute to the local observables, they commute to the Hamiltonian, and they are symmetries for classical symmetries for all practical purposes. Okay? And there also emerges the notion of a non-abelian chemical potential. We know that the chemical potential usually is a number operator, which in finite temperature field theory, which we add to the Hamiltonian, and it causes phase transitions between because of the number operator we have added to the Hamiltonian. But here I will try to tell you that there are non-abelian versions of this, which I'll put down, and I'll show you why they resemble this number operator. In fact, they are generalizations of the number operator to the non-abelian situation. And numerical work should surely, well, already at a calculation level, we can show that the existence of such a chemical potential will give a model for quark color confinement, different phases of color, and also these Floquet indices. So the correlation functions will show for suitable choices of chemical potentials, the Floquet indices you will have periodic correlation functions which will show these Floquet indices, and you can apply Floquet theory to this case also. So there is a set of rich results which emerge from here, but we have not, many of them are open because well, human limitations have surfaced in carrying out, investigating all of them and finding out that many of them are simply wrong. So we have to wait and see what happens. Okay? So let me go on. So let me remind you of, I think what again Rajiv mentioned about quantum physics. Quantum physics, normally we teach quantum physics using wave functions. I think that this is a very bad way to do it, because then you have to do a long argument what wave functions are, waves, this and that. But what is happening, as was I think emphasized by Rajiv, is that what we have got, the difference between classical and quantum is just that you have a probability theory in one case on a commutative algebra, and the other case you have a probability theory on a non-commutative algebra, and this is the basic difference. And how do I get from a so let me tell you what is a state. Again, reminding you of what Rajiv said already. In any theory, whatever be the theory you conceive of, there is first the set of observables which I'll call A. Yeah? So we normally take it to be some algebra, so we can multiply them to show how successive measurements go, and they have some algebraic properties. You may criticize algebraic properties, change it, but at this moment it seems necessary to carry on the calculations. And on this A, you have a state. What is a state omega? State omega is a positive linear functional on A. What does that mean? And it is normalized to 1 on the identity of this algebra. Okay? So omega on an element of the algebra A. So the algebra allows something called star operation. I am not telling you it's Hermitian conjugation, but it's an anti-linear involution. Okay? So A star star is A. Okay? And if you multiply it by some complex number, it also gets complex conjugated. It's like time reversal invariance. And omega is A star, on A star A is to be non-negative. Okay? This is the positivity requirement of a probability on any algebra. And we want the omega at 1 to be 1, which says that the total probability is 1. So, so these are two very natural requirements. And so, therefore, I emphasize again that omega is a probability distribution on A. So, what is the difference between commutative and what is the difference between classical and quantum? In classical physics, we deal with a commutative algebra. For example, if I have a particle on a line, you look at an ensemble of these particles, and they're described by some properties which are functions on the phase space, and these functions commute. So Fi Fj is Fj Fi. What do I mean by Fi Fj? Well, Fi at the point Qp of the phase space, Fi is a function on the phase space. Fi at the point Qp on the phase space is Fi at the point Qp. It's a complex number. Likewise, Fj, and the product is a pointwise multiplication. So Fi Fj at Qp is Fi at Qp times Fj at Qp, and use the fact that we know how to multiply complex numbers. So the algebra we are talking about for classical physics is this algebra where the Fi's, these algebraic elements commute. But if you go to quantum physics, the situation changes completely. Here, this relation is no longer correct. For example, Q and P do not commute. So the algebra that happens in quantum physics is non-commutative. Okay? These two properties, by the way, here, I have made a remark here. If you give me a state here, so a state by a state is meant a probability distribution in classical physics, and density, let's say, omega you can think of as a density matrix below in quantum theory. In fact, it'll all, by general theorems, it can be written as a density matrix. Now you may ask, what is wave function? I started by haranguing you not to teach quantum physics by wave functions. From omega, there is a canonical construction of a Hilbert space due to Gelfand, Naimark, and Siegel. Okay? It's called the GNS construction. It is completely common in the literature now. Okay? It's quite easy also. Okay? And when you do that, you automatically get these A's as represented as operators on a Hilbert space, along with the scalar product, which is determined by omega. So the wave function is a emergent auxiliary concept. It is not at the bottom of this thing. Okay? It is the state is at the bottom of the thing. Not only in the language I am speaking, but I think in our description of nature, that is the case. Okay? Maybe our description of nature is wrong. I don't know about that. Okay? But that is what it is. That is what the underlying reality of our activities. Sorry? Sure. Absolutely. Yeah. If you gave, as he said, if you have a wave function, suppose you have a Hilbert space representation of A, and you take a normalized vector from there, it defines a density matrix. So you can use the density matrix as an omega and redo the GNS construction, and you will get back the original Hilbert space. So it goes both ways. Okay? So whichever way you like.
Since you have non-commutative and commutative thing between classical and quantum, there is nothing like classical limit of quantum.
So I'll come to that. First, I don't know what is a classical limit of quantum. Okay? I don't know what it means. People say h bar goes to 0. I think that is nonsense. H bar is a unit. So the original Bohr argument, some number goes to infinity. Okay? So it's a number. In the later literature, you take S bar, action over H bar. What I will show you, and what people nowadays discuss, is that I think this idea emerged first, if I remember correctly, by a work by Ruel and Ranford, who showed that, who argued that in certain cases, uh, you can define what they call intrinsically define what they call algebras at infinity. Okay? Algebras at infinity are, in their calculation, is necessarily commutative. Okay? The commutative algebra then gives classical physics. So it is going to that limit, that is encoding the classical aspect which on which our cognition depends. Our cognition, we don't, I'll show you that there is no way you can measure non-commutative algebras. I'll show you in a minute. So that is one way of saying it. What I will argue here is that such a commutative algebra also emerges in gauge series at infinity. Okay? And it also emerges, by the way, in the horizon calculations of Chetan, very naturally. And I will try to argue that maybe the horizon can be transparent in some cases. Okay? If there is time, I'll show you how it happens in this language. I will not, by the way, I will not quantize quantum gravity. I don't, but certain aspects which are related to his large distance properties, I can address, maybe meaningfully. Okay. So here is one more explanation of what I mean by a state. State is meant nowadays as this such a probability distribution, both in classical and in quantum. So in both the cases, okay, you can also think of it as a density matrix in quantum theory, mostly, not always, but I'll show you why. Okay. So wave function is simply an emergent concept. So we don't have to talk about wave functions unless we are forced to. So we can keep going. Okay. So by way of introduction, let me look at a classical case. Okay. For a classical measurement, so for a classical measurement, for example, or for a particle on a line, we consider an ensemble of particles with some properties which are characterized by elements of an algebra, and a probability distribution rho of QP. Okay. Normally, we take this rho of QP as a measure in the Lebesgue norm, volume form on the phase space. Okay. So this is what we normally take to define this rho, and the average of A on this normalist measure acting on A of QP gives a number which is the application of a state omega on the observable A. So this is the average value of A for the state omega. So you have some observable and you have a state, and you have to put them together to get a number. Before that, there is nothing. They are just floating around as symbols in your book or something like that. Nothing. You don't know what that means. The pairing is what is important. This is a side remark, but here you may be puzzled. This in commutative algebras, there are no pure states which are normal. What is a normal state? Here I have given some explanation, but you also require this omega to be continuous in the topology of A. Okay? Otherwise, you will lose what we call subadditivity properties. Okay? So you need this omega to be subadditive. That is, if the sequence in A converges to some point, then the complex number you are evaluating should also converge in the same way. This is subadditivity, and it was a big task to prove this in the context of non-abelian algebras, which was done finally by Lieb and another person. In the classical case, it was quite well understood by Kolmogorov, and what happens is that such continuous functions, which are called normal, are all mixed. So they're actually density, they're measures on the line or on the phase space, not point measures in some interval, and they're all mixed. So there are no normal states in classical mechanics. That's something. What is a normal? What is a pure state? Pure state will be a delta function when rho becomes a delta function. It is a state. You can do the calculations, but it is not normal. It will not have continuity properties, and something will go wrong. Okay, so people do not use it in practice. Well, we know it. We know what happens in quantum mechanics. you end up by getting non-normalizable wave functions. Then you smear it with test functions, all kinds of junk. So the reason is this normality. So physically it seems fairly important. I don't know how you can dispense with it. So in any case, what I want to say is, so far as I can see no measurement problem in classical mechanics. Yeah. So, okay. I cannot see any measurement. There is a measurement problem. There is a problem because if you are going to measure only functions or elements of an algebra, you can very well ask, I will ask, what is the process of cognition? How do I measure, knowing these continuous functions? I know that there is a space-time with a dimension and where I am living. How do I do, what happens in the connection between the brain and that observation? I do not know how the connection takes place. I think this issue was recognized by Gelfand already in the 50s, where he showed that if you give me a commutative algebra like this, okay, with some further conditions, then he showed that the spectrum of this algebra, what is called the spectrum of this algebra, are irreducible. Okay. Let me not go into this. So this set of representations of this algebra has a natural topology, and that is that of a normal Hausdorff space. That is the kind of space we are dealing with open sets separating the points and so on. He showed that. This is a Gelfand-Naimark duality that I think is a hint on what we may want to go to. And this is what was developed by people like Alain Cohn or Mathilde Marcoli, Alain Cohn, over many years of work. And it ended up with this non-commutative geometry book and papers and so on. So it is not a trivial question. I still do not know what is the merits. I do not. So I would qualify the remark that there are no problems in classical physics to the statement that there is this fundamental problem how measuring functions on a phase space. I know that there is a Chetan sitting there. I don't know how that happens. I don't know. That is, I think, still an open question, very much open question. You may think it's irrelevant, maybe. I don't know. That depends on your interest. Anyway, let me go on. Now, what happens in non-commutative geometry is completely different. And this has been emphasized especially by people like Lanzmann. The problem is that in non-commutative algebra, there are unitary elements like this. Take any element of A and consider exponential I times A plus A star. That is unitary. So what do I do is, I just change A by UA U star. It won't change the full algebra because these are elements of the algebra. It will not change the algebra, but it will permute the elements of the algebra. So A and B, AB equal to C, for example, a relation like this will go into this new relation UA U star times UB U star. But this is again equal to UC U star. So this relation is preserved after the unitary transformation. So you don't know what, if I tell you to measure something A, I tell somebody, say, Sachin, measure A. He would not know what A you're talking about. It can be any one of these conjugated elements. There are further theorems by Alain that the orbit of this A in this algebra is dense. That is, you take all the things you get by conjugation like this, you'll get all possible A's which are possible. Then if you take all linear combinations, you'll get the full A like this. So he and Stormer clearly say you cannot make any measurements in non-commutative geometry. They say it in their paper, okay? And then they leave it. So, but a simple example is, if I tell a third party, go and measure a third component of angular momentum. How will I measure it? How do you know what is third component? Okay? There is no such thing as third component in the algebra. So what we normally do is cheating. Namely, we bring in a classical reference frame which provides the direction 3, and then we compare the two. But this is nonsense, because our description in nature, we should so far as I am concerned, all is quantum. It is our task uh, to extract information which is accessible to us by some process. Okay? It cannot be that we just add, like cooking, and you put a little bit of salt here, a little bit of sugar there, stir it. It cannot be like that. It has to be some coherent picture. So this is the issue that has to be addressed. Okay? Now,
But as long as you choose arbitrarily some z axis, and supposing you choose another z axis, we can compare the results of yours and mine.
but I cannot. How will I compare?
I will tell you some number, and you will tell me number.
How will you communicate the number? I don't understand. You may no. We have several observers. Uh, I am not talking about observers having a coffee and telling, I got this, you got that. I am not talking about that. But we don't do this anyway. Eh, eh, So I am talking, how do I tell in a non-commutative geometry? I say measure third component of angular momentum. I tell you, you would not know what is third component unless there is a frame which is common to both of us.
What we don't know that, like, how classical systems emerge from quantum.
No, that is correct.
Isn't that the same thing?
That is the statement, and the general picture that is suggested by people is that a classical commutative algebra will emerge at infinity. That is the picture. So I mentioned this at the beginning due to the work of Ruel and Lanzmann. There is the original paper on StatMech, and it was taken up by, if I remember correctly, Hepp. It's a beautiful paper by Hepp where he applied it to some spin system, which is a soluble spin system, and he showed how the state, which is really measuring only the operators which emerge at infinity, which he defines, are classical. It makes sense to do the measurements. He showed in that paper, but it is only for lattice system, some particular lattice system. Later, there is a whole slew of papers by people who do quantum philosophy, like Lanzmann. Then I think I have given the name somewhere.
But before that, also by Whiteman.
Yeah. Okay, there are other people who are concerned with this. There is a paper by Arthur Whiteman in one of his reviews, and our own friend Giorgio Mirci and a colleague of his had discussed this also, and they were using phase transitions as the triggering points for the emit. So they were really concerned. Both of them are concerned with super selection operators, which naturally can naturally give rise to commutative algebras. They both of them are already indicating that. So there are a group of people from physics also and from maths also who have addressed this issue. But is it settled? I doubt. Is it useful to do it? I'll try to show that in gauge series, it does give a set of results which can be, at least in principle, subject to experiments. Maybe wrong, it's okay. Being wrong is not sin, but at least it makes predictions. It doesn't talk about 10 dimensions and so on. You can do measurements and tell whether it is right or wrong, at least in principle. And maybe with refinement, something accessible to current experiments. That I had to see. It also gives stuff that last speaker talked about. For example, for helium-3, you can show that this gives rise to surface states for helium-3, and it also gives rise to transitions of chiral models on a manifold with the boundary. The effects are on the boundary, and there are transitions, and which are calculable. It will start emitting pions. The abelian modes, or the massless pion modes, the Goldstone modes, it will start emerging. You can calculate the rate. I have not done it, but you can. It is not a big deal. You can do the calculation. Okay. So I will now switch to quantum theory, gauge series. The reason is that it is in part motivated by the fact that they will suggest a model for observations with respect to these considerations. So these are my primary considerations, and these calculations will suggest some some particular models for observations where an abelian algebra emerges. Okay. So let me start with gauge theories. For example, let's say let me concentrate to SUN. Okay, and I look at a simple Lie group like G. By the way, G is not a gauge group. G is some compact Lie group which is sitting around. Okay. A connected compact semi-simple Lie group which is sitting around. It is certainly not the gauge group. Gauge group are actually something much more complicated, which I call script GOG, which is a group of maps from your space-time R4 to G. So it's a group of maps which is naturally a group because you can multiply them pointwise. So you can do the calculations quite easily. This is your gauge group. Now let me look at and the big player in this whole game is the Gauss law. I say that I am not trying to quantize QCD. In all over, give the Hilbert space for QCD operators, which I am not give. I am only talking about asymptotic quantization because that is much easier to do. So at a fixed time slice t, the Lie algebra valued connection, which is your gauge field AI, can be written as AI alpha. Alpha is a SU3 index, SUN index times lambda alpha, and the electric field, which also has an index alpha, and they are conjugate operators. And by lambda alpha, I mean the basis for the Lie algebra of G, the target group. Okay, so the canonical normalization is trace of lambda alpha lambda beta is twice delta alpha beta. Sachin chose it to be 1, I think. 1 alpha beta, it doesn't matter. It doesn't matter. Tau I over 2 tau, so you'll get a half. Okay. Now, the Gauss law is often written in this equation, where covariant derivative of EI plus J0 at x and t acting on the allowed quantum states is 0. So you have a big Hilbert space, which I'll call script H later, and this is picking out a subspace from this big Hilbert space. And Dirac gave this prescription to impose this constraint. But the constraint as written is fairly meaningless because the left-hand side is this EI because of the infinite number of degrees of freedom, or if you expand, the commutators involve delta functions. So these are not ordinary operators on a Hilbert space. They are distribution valued operators. And as such, this equation makes no sense. So what we have to do then is to smear the delta function, this left-hand side with some Lie algebra value test functions, which I will call chi0, which are, let us say, compactly supported. So they vanish outside some finite set. They are 0, and they are smooth. Okay? And let us take C infinity. So C infinity 0 is a notation that Rajiv was using. Okay? So let us say they are compactly supported. Then I rewrite this equation as minus the covariant derivative I put on chi0, then acting on E0, plus J0 acting on the quantum states is, so this object here I call Q of chi0 acting on the state is 0. Okay? And the trace is over the Lie algebra indices. So I have done a partial integration to go from here to here. This is the interpretation I give to this equation, to this activity, and this follows very much in the spirit of, again, somebody talked about Sobolev spaces. I think it was you again. Okay? This is exactly what is done in the context of elliptic operators on a manifold with boundary, because otherwise you will miss answer, you will miss solutions. So Sobolev already gave a family of norms. So and the burden of the distributional solutions of the elliptic equation is carried over by the test functions, which smooths it out, because this is in the dual space of EA. And you write this equation, this makes sense. And also the test functions I have chosen is compatible with Weidmann formulation. And you can check that this Q chi0. So this is the quantum Gauss law for all test functions chi0 which are compactly supported. And these are what is, and if you take the commutator of two of these things, chi 0 times q of chi 0 prime, commutator, operator commutator is equal to q of chi 0 with chi 0 prime. So it is a Lie algebra homomorphism from test functions to q. That is also fulfilled. And Sachin has said that he has found a good reference where why this is exactly what happens in the BRSA cohomology, or the so-called Chevalier-Eisenberg cohomology. I would like to know more about it, but let's see. Now, these are the what I will call as small gauge transformations. They close under commutator. Okay, so the commutator of one L0 and another L0 is L0, and the representation of L0 on the domain on the quantum space is 0. Okay, so that is the Gauss law. We can also define large gauge transformations Q of chi, but this chi are continuous Lie algebra value functions, not necessarily going to 0 at infinity. So expand the test function space to a larger set. Okay. So I write this, and after having expanded, I write this equation. But this chi may not go to 0, it may not be compactly supported. May or may not be, but they may not be compactly supported with test functions chi. So chi will approach some value as you go with the coordinate to infinity, which may or may not be 0. But in case it is 0, it becomes a chi 0, then it will vanish on the quantum space because it will become a small gauge transformation. So the representation of this q chi on the quantum state is by an equivalence class. Okay, all q chi where to which you add a small gauge transformation will all have the same image. You're quotienting out the algebra by this subalgebra L0. Okay. 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 So, and also here is some equation. Q chi is some q chi which may q chi prime is again a q chi double prime. Yeah, yeah, which implies incident, and also q chi with q chi 0 prime. Q chi 0 is q chi 0 prime. So this is an invariant subalgebra of two-sided ideal of the q chi's. And on the physical stage, any these q chi's are labeled entirely by the value of q of chi at infinity, which I have called q infinity 0 alpha lambda alpha. Okay, so only the boundary value will label the test functions in the q chi, and so I should have been careful. I should have given an example.
Three is automatic.
Hmm?
Three, the way you have written, it seems like it's an automatic fact.
I can't hear as I say.
The three, the way you have written, it looks to me that it is tautology. I mean, it's like it's true, but if it's satisfied for any chi prime, it will obviously satisfy for the point is that chi 0 is.
Chi 0 is compactly supported.
So, but it's implied by it. I think I'm kind of missing the point of what is the chi 0 is a normal.
So the chi q of chi with q chi of 0 prime is q of commutator of chi with chi 0 prime. Chi 0.
So the right hand side is not a chi, it's a chi 0.
Chi 0.
That's the point. It's not arbitrary chi.
It's chi 0 because multiplying a compactly supported test function with one non-vanishing, not compact, the product is still compactly supported. Okay, so it is an invariant subalgebra. So this equation automatically follows. And I think we did not say about this equivalence relation in our paper, but much of the other stuff we did. Okay. So I should have said put some slide that in case you take for chi, say lambda alpha. Okay, so take for chi as a specific test function, lambda alpha, which is an element of SUN, times unit, the constant function on space-time, space. Okay, then you will find, so chi I choose lambda alpha times unity, which is a constant function, 1. Chi prime I choose lambda beta, 1, and they commute this, you will find that this is equal to q of the commutator of lambda alpha with lambda beta, which is f alpha beta gamma lambda gamma, and the f's you can pull out. and you see immediately that you can realize the SUN algebra with these Qs. See, you get the full SU3 algebra with these Qs. But I did not tell, and I don't want to require that this chi infinity constant functions at infinity. This is a question that Chetan was asking Sachin, and I will not assume, I should not assume that they are constant functions at infinity. I don't assume that. So what kind of functions are they? Yeah. So here say some side room. I'll come back to that issue. Now, the major thing here is in any quantum field theory, gauge theory, there are two things. One is that you have something they call script F, which is a local field algebra. The field algebra. The field algebra is not composed of gauge invariant functions. They involve the connections which are not gauge invariant. In a non-abelian case, the electric fields which are not gauge invariant, and many other things which are not gauge invariant. That is what they call the field algebra, and it is known to be important in constructing certain super selection sectors, to which I will come in a minute. Yeah. So, but in this F of the local field algebra, there is a local which is the gauge invariant subalgebra of A, the F. Okay, is sitting inside this F, and these are gauge invariant. And because of locality, you can again Sachin explained it nicely. You can restrict by because of the locality, this Q chi commutes with elements of A, the gauge invariant operators. Okay, we explained why, because the local operators are smeared with test functions in a local region, and the commutator of this Q with the local, that those test functions will be sensitive only to that compactly supported region. So you can restrict Q chi to that region and say it is 1 outside, okay, or 0 outside. No problem. Okay. So you will find this equation. If you want, you can do the calculation which we have done, but this is true. It also, for the same reason, it leaves equations of motion invariant. Okay. For the same reason, equations of motion are gauge invariant, but they are also local equations. If you start writing non-local equations, I'm off the game. Okay. I don't know what to do. Okay. Then there are problems with causality, all kinds of, I don't know. I don't want to discuss them. Now I come to super selection sectors.
So just one question, this Q chi, the definition of Q chi that you are using, that was borrowed from the one that was defined for compactly supported.
Yeah, so I extend it to non-compactly supported test functions. You may ask, why? How can I do this? Okay, okay. As I told you, I think somebody asked this question. It's a good question. Is it relevant? Is it correct to do that? Can I've given some field operator and I'm changing the test function space to a larger one. Can I do this? The answer to this question is something I don't really know. Okay? Thought about, but the consistency is the persuasive elements of this argument is that it enables me to represent operators corresponding to electric charge. E dot ds, I don't have to write E dot ds at infinity. That is not an operator. It is something you're writing by hand. It will, if its commutator will, everything will be 0. Okay? If you write E dot ds at flux at infinity is charge. It's a classical statement, but quantum mechanically it makes 0 sense. Here I can realize all the elements of SU3, and operators I find are producing SU3 Lie algebra. So there are supporting evidence, and further supporting evidence is that this algebra is produced by it produces a commutative algebra, and it is also produced by something which I don't have time to discuss, what people call nowadays algebraic quantum field theory people use as string localized fields. The string localized fields are quite remarkable because it requires no gauge fixing whatsoever, none at all. So the construction is not complicated, and they showed many of the known results which one knows by other considerations. So there are supporting evidence for this activity. I don't know the answer really. The only thing I am reminded of is, again, you asked me this question before, I think. Hmm.
That was some time back.
Yeah, there is some, this Gelfand triple. A thing like this, Gelfand triple, you have a unbounded operator on a Hilbert space, then it has a domain. Then the spectral resolution of this operator is, because it's unbounded, it might have continuous spectrum. How do I write the spectral resolution? Then the domain has a dual space. Okay, the dual space is not in the Hilbert space. There is a dual space. The dual space will have a nice value on the domain. And then the spectral resolution in those papers of Gelfand is solved. This appears to be somehow connected to that. But I don't know I have no control over the math here. That brings another question. Maybe one of you knows the answer. Why is heavy precision in mathematics necessary to confront nature? I don't understand. Because experiments are full of errors, the dirt, this and that. Why do we need this kind of maths and precision? And seems to be important in, say, many contexts. I don't know. Okay? What is the level of precision we need to confront nature and make some kind of a formula for it? I don't know. I suspect it is because experiments nowadays isolate the system more and more, okay, from the surroundings. To the degree of isolation that they do, the precision of the mathematics should, our precision of our thinking should also match that, I think. But I am not sure. That is another puzzle in this context. Okay? To me, it is a puzzle. Okay. So, I want to come to super selection sectors. I should finish by 1:15. 1:15. Yeah, am I right? I started 10 minutes to 12. 1:05. I will finish it off. So irreducible representations are of A local. Irreducible representations of A local are what we call super selection sectors. In physical states, the super selection sectors are labeled by a complete commutative set of operators in the model, in the sigma model. Okay, I did not say that. Okay. So I said that the chi's are labeled by the value of chi at infinity, and here I am assuming, not assuming, actually, this chi infinity are functions on the two-sphere at infinity. So we are compactifying spacious rise by a two-sphere. You may ask, why am I using two-sphere to compactify? There is again good reason. If you look at the string localized fields which they have done, naturally S2 emerges in their calculation. You can also compactify with CP1 or point compactification. They will give different results. Okay? But their calculations suggest that S2 is the appropriate one, and it can also be made into a compactification or on with the Poincare group acts, then it will become a de Sitter space. So it will enlarge into a three-dimensional space, which is de Sitter space. So there is some consistency, but maybe it has to be changed. So anyway, I am taking S2. So this chi infinity are functions. Is a sigma model we are getting. Namely, chi infinity are functions on S2, and it's a non-abelian sigma model. The chi infinity are valued in a Lie algebra. So we get a non-abelian sigma model at infinity at the Lie algebra level. Okay. So how are the super selection sectors classified? Okay. They can be labeled by, as I say, complete commutative set of operators of this kind. Okay. So lambda 3 and lambda 8 for SU3, okay, and the Casimir operators, okay, so you have to take the center of the enveloping algebra. Here the Casimir operators, lambda 3, lambda 8, which are in the center of SU3, Lie algebra, and you can label the states. Okay. So, and also the two Casimir operators of SU3. Okay. And then you can also label by functions on S2, which are commutative. Okay. So you can label the complete commutative set which you are diagonalizing by this set of operators, and they are labeled by a commutative algebra because the complete commute is a commute. Dirac in fact picked it because it is commuting, and the functions I have added also commute. So what you are getting is a commutative algebra at infinity. If, necessarily so, these are labeling the asymptotic states, asymptotic observables. The claim of Sasha and I is that this abelian algebra is requires is the one that is required by borification. Borification is how does the abelian algebra emerge? We are suggesting that it is this process that happens in gauge theories. In some other theory, I don't know, but in this theory, this is how it is emerging. You may, some of you, well, this thing you can forget. This abelian algebra, you may ask, what is the topology on this abelian algebra and so on. You forget it. It is, we take it to be basically it is a C-star algebra, but never mind. Now, the major point which I already said is that the color transformations which we can write down are large gauge transformations, and they are in this full algebra which I wrote, full algebra of this Q chi labeled by this Q infinity, not the diagonalized operators alone. So the diagonalized operators are the ones which are mutually commuting, but they don't span the SU3 D algebra, SUN D algebra. So, but then what happens? Suppose I apply a color transformation, arbitrary color transformation. It will change the eigenvalues of lambda 3 and lambda 8 because SUN is non-abelian. So what happens? You change the superselection rule. The change in the superselection rule is what we call as spontaneous symmetry breakdown, anomaly, what else? Whatever you want, like, and it is the one that leads to index theorems. So the operators which change the large gauge transformations which do not commute with lambda 3 and lambda 8 are change the superselection rules, and they are said to be anomalous or spontaneously broken, and they are at the basis of the index theory, whatever you want to do. They are the basis. So I just want to say the superselection rules are quite important. For example, the Kramers-Vannier duality, where t goes to 1 over t. Why is this partition function the same? The transformation from t to 1 over t is you're changing the state on the observables. This transformation is changing the superselection rules of the algebra observables in the finite temperature field theory, in the Kramers-Vannier duality. But that transformation happens to be isospectral. That is, it preserves the spectrum of the Hamiltonian, not individual ones. It's the spectrum of the Hamiltonian. So the trace of exponential minus beta h over t is not changed. Now, there are many. So Kramers-Vannier duality is that. I just want to remark, is maybe quite important. There are plenty of such operators you can find which are isospectral but changing the domain of the operators, which are changing the superselection rules. In all of those cases, you'll get the partition function trace will be exactly the same because of the fact that they're isospectral. That's all. So it seems to me that Kramers-Vannier duality is an illustration of what I'm talking about here, which is.
Just to understand what you're saying, so the Q that you're acting with will basically change the global color chart in the state.
Yeah.
Correct? But so that would be something that one would consider as a dynamical prediction of the period. So in this
yeah, here it is necessarily coming because of the fact that you can only diagonalize a complete computing set. No way you can diagonalize anything else.
Right, but I mean, in QCD, for instance, we expect that only the single sector is there. So it becomes confined.
So you have to show me, I have not seen it, what are the QCD operators, not by mouth. You have to show me how they act on the Hilbert space and what you are diagonalizing.
Right. I mean, that is too tall an order. Right? Because we don't know how to solve QCD.
No. Here I have done it. We have done it. It may be wrong, But we give you
Whatever you have shown is roughly, okay, like you have to show it at the level of the interacting angles theory, right?
this is a fully interacting theory.
But then you have to do renormalization and everything. But the charge that you are defined, it's more of a schematic expression. So you have to actually do the renormalization and all of those things in order to actually
No,
write that.
the local algebra is done, no?
But why is it the Q that you are defining? It has, like within the full interacting theory, it will basically contain interacting things. So that means that you need some form of vectorization renormalization in order to define it, which you can only do in maybe perturbation theory or something. Or in lattice. So for me, this Q sounds like it's a prescription that you would like to have, but it's a dynamical question whether states of this kind are there.
I don't know. Maybe you have some point. We can discuss. Huh?
Yeah.
I don't know in gauge series what else you can do. Okay? Otherwise, even in U1 electromagnetism, show me the operator for charge. E dot ds integrated at infinity is not an operator. That I will defend my. So write the operator. I don't know what it is.
I'm just saying that, like, in order to make it, so typically what we do is that we assume that the hyperspace of QCD contains only, and global charges which basically can rotate the cover charge don't exist. It's basically there's no proof, but it's
I write you so I give you an operator in free QED where I can do all the.
But I'm saying that, like in QCD, for instance, it's a confining theory, it's not appealing theory.
I don't know that is confining. That appears to be a slogan. That appears to be a slogan.
But it's, there is a whole archive dedicated to it.
From what I understand from lattice people and others, confinement as a moment, at this moment, is a slogan. It may be true. I don't know.
Lack of proof is not lack of evidence.
Anything. I don't know of any convincing argument that color is confined. Convincing argument. I have not seen it. I have talked to people doing it. I have asked several other people, and they say, "Oh, how?" Then they say, "Who says color is confined?" No, I don't say color. Immediately they go into the defensive mode. So I don't know. It may be confined. Could be. Then that will mean, to me, that will mean that a domain Hamiltonian is an unbounded operator. So if you say color is confined, it should mean that will be some proof I am not capable of. The Hamiltonian is an unbounded operator, so it has a domain. It doesn't act on the full Hilbert space. So the color charge sector of the Hamiltonian cannot be in the domain of the Hamiltonian. So if you apply Hamiltonian on that, it will diverge. I have examples of this for a particle on a circle. Very simple. So I can show it to you. That has to be the proof. I have not seen such a proof. If you show me the proof, I will be converted.
But I think the statement that you're making is, I would say the evidence for it is overwhelmingly against it, right? In the sense that we don't see colored particles because.
And that doesn't. I will give other. I have given. You can make other models, which may be wrong, but they also give color not being seen.
As far as QCD is concerned, we are already there. So there is no need to go to the boundary of space time.
The boundary states can be in a ball. For example, for helium-3, where you have it is a finite ball, can do it. You can do it in any ball. This calculation can be done in any ball. So, because what is infinity here is what you mean by locality. So, if you take a causal diamond, the boundary of the causal diamond can be your boundary. No problem. You can do the quantization in that causal diamond. That is also possible. Okay. So, okay. So I should tell you what is this Takes. So this is my final thing. What do you mean by Takesagi duality? People are complaining to me that I think Rakesh and somebody else was complaining that they don't know what it is. It is rather simple, but the trouble is, it is simple generalization of what people call as semi-direct product of groups. So the Poincare group, for example, representation theory of the Poincare group involves semi-direct product, where the Lorentz group acts on translations. This is a simple generalization of that. So in the case we are interested in, where the Hamiltonian is going to, the abelian group, exponential ITH is going to play a role, the Takesaki duality is extremely simple. Okay? What is it? You take the real line and it is going to act on the field algebra F. How is it going to do? T, first I take T, it's a real line, it's a group under addition, and I take a representation lambda T of T, and lambda T acts on functions of tau, which is L2 of R. So just quantum mechanical line with the standard volume form, and it acts by translation. So this is a left regular representation of lambda T. So this is abelian representation we should all be familiar with. Now I want to make this T, R act on the field algebra. This is denoted in the literature by this funny symbol, inverted thing here. And this is generated by, so what I do is, I take this T, which is acting here like this, I take a unitary representation of lambda T, ut, which is T going to exponential I tau h, th, where h is your Hamiltonian. Now, R acts on F in the following way. There's a, you take the field elements of the field algebra F, tensor with 1, okay, ut, which is this operator, tensor with lambda T. This whole thing is acting, so F is in F, T is in R, double prime, forget double prime, it is to get a von Neumann algebra, and it is acting on a Hilbert space, which is the Hilbert space H of F, on which and H and everything, which is acting here, and L2 of R is started from. So the elements here act on H cross L2 R, and you look at the bracket here means you take all their products with the relations I have given you, and that generates an algebra, and that is this algebra left, okay? And they left here. Okay? If you replace this F by a group, you will get simply a semi-direct product. Okay? So an abelian semi-direct product. Okay? So this is a direct generalization of abelian semi-direct product. If there are more questions, you should ask. I think Rakesh was the one who was complaining. I think somebody else also complained. I don't know who. Okay, I want to. Now, going to my end thing, we notice that Q chi commutes with the local equations, local algebra, and gives rise to a lot of classical conservation laws. So, and I am thinking of this Q chi as something that the experimentalist choose. So the chi is at the command of the experimentalist, and he's going to couple to the local system. Okay. So how am I going to do this coupling? This Q chi presents also equations of motion. So let E0 be the energy scale of Q chi. Now you notice immediately that the evolution under exponential IT, H plus E0 Q chi doesn't change anything to local algebra, doesn't change anything to equations of motion. So this is a perfectly good operator to evolve your operator. So and this acts on your Hilbert space H. Okay? All these operators act on H, where H has the property that quotients out small gauge transformations. Yeah. So I want to do a duality because Q chi is acting on H, just like I did for exponential ITH. I'll introduce something which is like a Hilbert space R prime. Okay, R prime is a new L2 of Hilbert space of L2 functions, where R prime is an abelian algebra of which is going to take is given the task of implementing the action of Q chi, and I'll introduce unitary operators exponential IT Q chi. So now, where is it? Somehow, yeah. So the Hilbert space has now got enlarged with an extra L2 of R prime. Now let me see what happens if I take the diagonal subgroup of R cross R prime. R prime is the new group I have introduced, and let me see what happens to the diagonal subgroup of TT corresponding to these things. acting on this F here. So Tt, they are the same. So it will be exponential It times H plus E0 Q chi. Okay? It will add this extra term to H. Okay? So the action of R cross R prime diagonal on F is this object here. So, and it is acting on this triple tensor product. H, L2 of R corresponding to time evolution, and L2 of R prime corresponding to this Q, the gauge transformations which I have added. Okay. So the chemical potential has automatically been non-abelian chemical potential. An extra term has been introduced in H, and this extra term is what I have called as generalized chemical potential. Okay. It has all the properties of the number operator, but it is non-abelian in character, unlike the abelian case. And this is what I have called as non-abelian chemical potential. Okay. It can be added. Okay. It won't change. It won't. You will not notice in classical physics. E0 is some scale which is associated to the experimental setup. Q chi is dimensionless, so I need some object there which has a dimension of energy, and E0 is the scale of the coupling between the two things. Okay. Okay.
That's used by hand. That's introduced by hand.
E0, the scale is introduced. I think there are issues here. What do I know? So it depends upon the experimental setup, I suppose. Then there must be some analysis which I am unable to provide. It may depend upon the power of the electric field I use to detect whatever is coming out of the LSC data. I don't know. Okay. I have no control over these things. Maybe a person like Indumati may be able to tell me. I don't know how to. I don't know how to think about it, except that I know that it has to be there. So now what I want to do is something. So the Hamiltonian has become H plus E0 Q chi, but now I am going to claim that there is a way of making a unitary transformation on A local, which I have written down, to A prime of local, which has the remarkable property that it actually commutes with H plus Q prime, H plus E0 Q, this object here, exactly commutes. This is related to what is called Takesaki duality. So you don't need to know too much details. I will not worry you with some details. So I will take the field connection field A and smear it with test function F. Okay. This is well-defined operator on the Hilbert space, and the Fm must fulfill some properties relative to the Q chi I have added to H. Okay. So it happens that I have so added it that this Q chi and AF are conjugate variables. So we can forget about okay. Very briefly, if I make a gauge transformation on AF, what happens is Q chi makes a gauge transformation on A, you get two terms. One is the covariant derivative of chi. What you get a priori is this covariant derivative, which consists of this term and that term. The second term, by cyclic trace identity, is this object. But by choice, these two commute in the region where this F is supported, some small region where F is supported. So it is 0. And by choice, these two are normalized so that their product integral, where is it? Integral is 1. So I have written it down. By choice, this is only a local statement. The chi has to be distorted, chosen from a whole lot of chi's whose infinity value is controlled. But locally, I can do what I like, and I just choose this integral only involves local data, and I choose it to be 1. Okay. Then these two are conjugate variables. So I found a conjugate variable to Q, okay, minus I. So I look at this A prime, which is the conjugate of A. This is exactly what is done in the Takesaki duality. So what happens if I commute it with exponential IT E0 Q chi on A prime? This Q chi goes and translates A by 1. Okay. So you get this object here. A is translated by 1, A prime defined here. It is translated by 1. So you get this extra term, which is exponential minus ITH. Okay. So I can put this exponential ITH on the right hand side, and you see from here that h plus G0 chi exactly commutes with A prime. You may see in the Pennington Longo Witten et al. Paper also that they have a construction like this for de Sitter space, where
But then there they have the Hamiltonian of an observer. Here, on the other hand, this E0 Q that you're adding, it seems very ad hoc in some way, and also it is being added. So there are two things you're tensor producting with. The L square R, there are two copies of L square R that I saw. But in their construction, there's only H times.
that's correct. That is a more important remark. So that's why I put variant Takesaki duality at the beginning. This is not exactly Takesaki duality.
Also, like the time evolution is using the Hamiltonian is time evolution. So, but you are formulating the time evolution on the gauge theory side as a cross product.
No, wait a minute. I'm not going to change that standard. I will not change the time evolution of the observables under H. You'll see in a minute. The reason I am doing this construction is something different. This equation means that as long as I look at states, I look at states which are generated from the vacuum by A prime. I can look at the states. You have to do some normalization. Then on these states, H plus E0Q chi will not evolve it at all. Vacuum, I am assuming, is, I guess, has zero eigenvalue, but the sum. Hamiltonian is zero and there's no electric charge or anything, no color charge or anything. Okay. So the standard time evolution with the exponential IHT will be equal to this evolution here. Yeah. These things do not individually commute with this A prime, but the sum commutes, okay, not individually. So this is a new point as compared to Edwin. So the local evolution of these operators under exponential IHT, which is a local observable evolving, can be detected by what is happening to chi, which is supported at infinity. So the claim is that the infinity measurements or the superselection sector operator measurements will give you information on what is happening locally. Okay? I can do many things with this. I can make chi time dependent. So chi can be switched on and switched off. Yes, if there is an experimentalist doing such things, and you can see what is happening locally. So this is a model, and we are all the time involving an abelian subalgebra. The operators I am writing, so Q chi, okay, A prime is something. So the operator, I have a complete commuting set. So this equation is true on the states I have written down. And the complete commuting set is also diagonal on that state. It could happen, it will happen in general, that this Q chi changes the complete commuting set and takes you to new supersession sectors. That is another story. But anyway, this equation is correct. It seems to be correct. So local measurements will give me data on infinity. So this is my major point. Okay? So I want to finish off. Okay? As I told you before, this model does have experimental signals. Okay? In other papers which I put down in the net some time ago, it has experimental signals in gluon physics, in pion physics, theta vacua. There is a paper in theta vacua which seems to have very strange properties, including affecting beta decay spectrum and CMB, which can be, I think, calculated. I have not done it, but let's say one would like to do it, so one has to first figure out exactly how to do it. Then you can say the CMB spectrum will be this. So it can be done. Okay. I think it can be done, but we are not done it. So let me finish off by provoking our friend Chetan here. So let me take. Is there a chalk here?
I think my question is even before this. So he's provoking you.
Where is the chalk?
I'm already provoked.
Okay, let me take simplicity 1 plus 1. it's not important, and take the Rindler wedge. This is Rindler wedge, right? The Rindler wedge is globally hyperbolic. You can take time slice here and go all the way there, and you can write a quantum field theory there. And the boundary of the quantum field is this and this. So the signals from here, so you can do the things. If you put a gauge theory here, the signals from the gauge theory will affect the data here. This is your boundary. So this is your chi infinity, the S2, not the boundary of this Rindler wedge, boundary of Rindler. Okay. The inside is also globally hyperbolic. You take mass shells, and the time evolution is given by scale in the mass. It's also globally hyperbolic. You can write a gauge theory there. This is boundary stage. That will also affect what is happening here at the boundary. So anything happening in the boundary, in the bulk here, will affect the boundary here, and the boundary in turn will affect what is happening here. So information from here will pass to here. Yeah. I have done the calculation for the Rindler case. What is happening is that you have three objects. One is the H Hamiltonian in the interior H prime. Here there is a Hamiltonian H in the bulk here, and the boundary stage which is given by a common set of observables Q chi. Yeah. And they have corresponding vector states, and they are all entangled. There is a triple entanglement. So if you touch one, the other two will shiver. So you can see what is happening. So although classically no light ray can pass this thing, it seems to me in our model that it can pass, right, by entanglement. You can detect what is happening in the inside. I can also do it for Schwarzschild in the same way, because inside for the Schwarzschild, I have to take this Gilstrand Pine-Levi coordinates, which gives you a time slice, not a time like Killing vector, but it gives a time slice. That seems to be enough to write a gauge theory. And again, the same thing seems to happen. So here, for the Schwarzschild case, I have not done the calculation completely to my satisfaction. So, but I think I can do it, because the change of coordinates are quite simple. All that you need is a gauge theory.
Two things that I bothered. Like one of them is that when one constructs these the kind of H plus E naught Q type of thing that you're constructing, so that usually that kind of cross product construction is done when you want to construct a gauge invariant observables, where the system is a gauge theory and you want to have an observer, and the combined system needs to have gauge invariant observer. That's when you do this combined. So that's the total charge effectively that you're defining, and then you more it out roughly, and that's essentially what this cross product is.
So here,
and that sort of thing I haven't found it, but I wouldn't say, for instance, that that's the same thing as holography, because holography basically means that all the charges are only at the boundary.
All the charges are at the boundary. That's true in gauge series.
For instance, you have local observables.
Local observables are there in both.
Gravity, there is no.
Rindler wedge, there is a local observable.
No, but once there is dynamical gravity, you don't expect there is any local observables at all.
I am not quantizing gravity.
Yes.
This is the.
You're not doing holography, is my point.
Sorry?
Then you're not doing holography, is my point.
It's a holography for the gauge theory. I don't understand. I have a fixed background. In this case, in Minkowski, I have done. Okay?
Right. I'm just saying that holography means that there are no local observables in the bound.
I don't know that.
It's a very dramatic thing. So that's the reason why.
No local observable. No, then it is not local observable. This is not holography. You can forget the name. I'll call it holography prime. No problem. But by the way, Witten's calculation has local observables. He has the entropy of the local observables to the entropy, the maximum entropy state coming from type 1 algebras.
What he does is he adds an observer to the system, and then the total thing he makes some statements.
Here, the observer is Q chi.
Yeah, so you have an asymptotic
Observer here also.
So that's what your Q is.
So that is quite similar.
Yeah, it's similar, but I would say it's more like constructing gauge invariant observables in this system. That's what it's are anchored to the boundary. That's what it is anchored to the these boundary charges.
No, the observables are local. They are not at infinity. That's not.
No. I mean, if you want to have, let's see,
So if you say there are no local observables in holography, I'll call it holography prime, no problem. But because I am not changing the local dynamics at all. QCD, for example, asymptotic freedom, all those things I am not touching.
Freedom is fine, but the cube that you're defining, I'm not sure that it actually can move the space because they will create color.
What will happen is, okay, what will happen is something more interesting. The quantum state will be consisting of some vector psi in the.
You have provoked me, but I don't want to provoke you. So that's really.
So anyway, you start some complete computing set of lambda 3 prime, lambda 8 prime, which is diagonal, right? So the state I am writing is some psi times this, for example. Then I am looking at the operator h plus q e0 q chi. This is the evolution I am looking at, right? This is evolving it. The evolution I am looking at with the chemical potential put in is under this operator. Okay, this q chi need not can change this. So for appropriate q chi, what happens is that this elements in one Karta subalgebra start jumping to other Karta subalgebra, and appropriately chosen q chi, you create an ergodic orbit in the space of q chis, in the space of Karta subalgebras. And the time scale is really ergodic. So if you take a time average, you get 0 for colored observables, which I checked. So you get. So the question is time scale. If time scale is small, time scale is small compared to the experimental time scales. Experimental time scale is about 10 to the power minus 23 seconds, right? And if this q chi E0 is appropriately chosen, it is simply, you will get this ergodic, you will realize the ergodic hypothesis. But so the color confinement will be in the phase where the orbit created by this is ergodic on this. The nature of this ergodic orbit, I don't know. I tried to talk to mathematicians, but I don't know. It's like winding line on a torus, but I don't know how to do it. Remark is, you can ask how many states, if I take the entire sigma model states at infinity and see what is the maximum entropy I can get from that, it fulfills this. The number of states you are getting for large SUN is the order of exponential n. So the entropy is order n. So from what I saw in people doing string theory, this is the kind of thing they say they have got the entropy. Here also you get it. It's simply a property of Grassmannians and their dimensions. I am very reluctant to call this confinement. It is something, this is a property of Grassmannians. But just a remark, final remark, then I stop, shut up. The final remark is that you can also choose this object so that this orbit is periodic. No problem. You just choose the ratio, the eigenvalues of this chi to be rationally related. You'll get a periodic orbit. The periodic orbit has the property that the correlation functions are periodic. And that for the 2-point function, for example, you can do the calculation and you will get Floquet systems and you can do a Floquet analysis. I have not done it, but it can be done. So this is where we are. We are still exploring some. We want to be sure before we write a paper. We want to be relatively sure before we write a paper. So we are working on it. There may be mistakes. There are mistakes. We are human and we make mistakes. What did Antonio Machado say? There is no pathway. It's a traveler poem. There is no pathway. There is no pathway. You only make the path by walking. Okay? So, el caminante. You have to walk. So we are walking. If it's wrong, okay, throw it away. Okay? You see. Okay, I'll stop there.
Yeah, so I think we are quite late. Maybe if you could.
So this A prime new algebra which you are constructing is a function of E naught value which you are putting. Right? So as a function.
It's not a value. No, it doesn't depend on the scale.
Which one?
A prime doesn't depend on the scale.
No, it is taken by the cross product, right?
No, A prime does not depend on the scale. It depends on this compactly supported smearing function, any compact support, with the property that whatever q chi you are operating with as a chemical potential, in that compact region, it fulfills, it commutes with that restriction and gets normalized to 1. That's all. But there is no scale there. And it is causal, star operation can be fulfilled. So there is no problem with those things.
If I change E naught,
You can change q chi, you can change E naught. You can change E naught.
can I go to 0?
You can also go to 0, then you'll get back the original system.
So original thing which is there, once you have a small value of E naught and change it, there's something else is happening at the other side, right? I want to understand that.
You want to do, but if you are asking how, so, let me take the case of Riller wedge, which is easy to handle. And you take small E0, I think you can do perturbation theory. Quite this standard time order perturbation theory you can do. This is a good question. We can do the calculation. I have not done it. This particular idea I have not thought about. Making E0 small. By the way, I have also found out that
Make 0 small and larger and larger.
see what happens. Yes,
What is it I can measure?
it's a very good question. I have not done it. Is it?
In reality, that's what we are doing. But we are going to have instrument which is going to tell me what is my value.
Yes.
And that is going to tell me what are the things I can measure.
Yes.
What accuracy I can measure.
Yes.
The observables which I can measure to what accuracy is what we are finding.
Yes.
I want to compare it at that level.
It is a very good question. I have not done it.
Okay, I think let's thank the speaker.